getting up, and then from here on it gets down, right? I like Wednesdays, especially Wednesday evening. Then it goes into Thursday, and the weekend is coming closer. So slides covered all autocorrelation and cross-correlation, and we had, besides that, we had good exercises and discussions. Before we jump today into geostatistics, I want to ask you whether you have any immediate questions regarding what you learned yesterday, or what crossed your mind and didn't let you sleep. You know that feeling, right? Somewhere you hear something or you read something and that really catches your mind, and you fight battles with your blanket at night and can't sleep, right? But that's good. That's when it catches you. So any questions about yesterday? No? Then I want to ask you, with the format, we do the exercises, the computer exercises at the end of the morning and also at the end of the afternoon. Are you happy with that, or shall we change anything? The format of the computer exercises. Are you happy with that format, or do you want to change anything? It's fine? Good. Very good. Okay. So, who has ever worked with semi-variograms or heard about it? Heard about it? Good. Okay. So semi-variograms is a tool that has been developed in geostatistics, and that is one of the most of the earliest tools. And semi-variogram is always considered a little, oh, this is just the baby stuff and so on. But to me, a semi-variogram remains one of the most important and most informative tools in data analysis. So I hope I can convey why I think it is a very simple but very effective tool. And we have met already the sister of the variogram, semi-variogram, that is the autocorrelation function. So what we learned this morning, we should with one foot stand on known ground. So what is semi-variance? In simple terms, it is values separated by short distances usually differ less than values separated by long distances. Well, that sounds familiar with autocorrelation, right? Here we talk about vary, and in autocorrelation, when we walk down the aisle here on these tiles, we said observations taken closer together are more similar than observations taken farther apart. And in very simple terms, it is half of the average difference squared between observations separated over a given distance, called lag. So this is what the equation is. And this statement we will see in one of the next slides in formula signs. It is another form of autocovariance, and the calculations, the procedures are very similar to autocorrelation. One big difference, autocorrelation is mostly used for serial data, so for transect data or for time series data, one-dimensional data. That is based on where autocorrelation was developed, in what discipline. They mostly dealt with serial data, whereas semi-variograms also deal with multidimensional data, two-dimensional, which does not mean that we cannot also calculate an autocorrelation for multidimensional data, but it has just not been done a lot. We can answer questions that are very similar to those from autocorrelation. So should samples be taken randomly or at uniform regular distances, regular intervals. So shall we just put out a sample at every tile and then also go in that direction? Or can we say we take one sample here and measure it with a GPS and the next one here, similar distances, but not regular? How close together should samples be taken? How far apart must samples be observed to have their absolute differences in magnitude remaining constant? And do soil or crop variations differ with direction of sampling? So whether when we have a two-dimensional data set, is the computed semi-variogram different if we just calculate it in this direction? All observations that go in this direction, or the same observations, but we now calculate them all in that direction. So is there a difference? How many samples are needed for a reliable semi-variogram? How can a smooth curve be identified to describe the calculated points of the experimental semi-variogram? And when is a semi-variogram suitable and when the autocorrelation function appropriate? In what respect does their information differ? How does the semi-variance change with the size of sampling volume and the sampling domain? So scale triplet again. How can we determine with a semi-variogram whether a spatial or temporal process is scale variant or invariant? Here are now a few equations. These will be about the only ones in this set of slides. You know this equation. You are very familiar with it, maybe except this one and this one or so. But this is the variance. And now, little exam question. Is this the population or sample variance? Good. You got it. You got an A. Similarly, we compute the variance. We can write it in these terms, that we take an observation and we subtract it from the average value squared. The experimental semi-variogram is calculated. So this is exactly in formula signs what we saw 2 slides ago, or 3. It's half the average difference squared between observations separated over a given distance. So here we have that difference between observation A at location xi minus A at xi plus the lag. So the difference between these two observations, that difference is squared. And then all those differences that we observe for this distance, so all pairs, 1 on 1, 1 on 1, 1 on 1, all those pairs that are separated by the same lag, averaged. Those squared differences averaged. And here, well, this is made by the geostatisticians. We do not use n for all lags, like in the autocorrelation equation. We use the particular number of observations, of pairs of observations in that lag class. And that is, you can blame that again on the history of where the semi-variogram was developed. It was in geosciences, and there were not infinite numbers easily collected. There were limited numbers, and they had to be obtained with hard sweat, soil coring, and so on. So limited numbers, and that's why the geostatisticians said, well, for us it matters if we take the absolute known pair of values or just a huge number, n. They are not engineers. We are the electrical engineers who have thousands of numbers in one series. So here it matters. So keep that in mind. And that's all it is. Now the interesting part is then the shape that is derived by this behavior. And we will learn interesting things about that, what that shape tells us about the original data. Here, again, a little cartoon on how the semi-variogram is calculated. So we have and I simplify it here. Later, I have a little scheme for a two-dimensional data set here, just that we get our foot on the ground. We say we use a one-dimensional arrangement of points. And for leg 1, we compare x1, the point, the observation at x1 with the one x2. And then x2 at x2 with x3, x3 with x4, and so on. So nothing different than in that comparison like for the autocorrelation function. And we do then the same thing. And then we have for leg 1, we run all these comparisons. That means the differences squared and averaged for that leg class. Oh, and I forgot, and divided by 2. So that's important. We then obtain this variance value, the first leg semi-variogram coefficient. Then we go to leg 2. And what does this tell us? Variance is higher. So if we skip one, so if we increase the distance over which we compare observations, they get more diverse. The differences become larger, less similar. So same concept as an autocorrelation. They keep increasing with increasing leg distance. Here we have the cartoon going until 3 legs. And then in the ideal world, at some point, the differences do not increase anymore. They stay on a plateau. Regardless how far we separate observations, the variance does not increase anymore. We call that the sill or the plateau. And for a textbook data set, that sill plateau level is very similar to the total variance of the data set. So whenever we have the variance, even at short leg distance, sometimes being at this plateau already, then we have a random data set. Total variance and the mean, they both describe the data set. In this case, we have a structure. Closer sampled observations are more similar, have a smaller difference than observations separated by a larger distance. We use certain types of models to describe the shape of an experimental semi-variogram. And here we want to look at different components. We distinguish between 2 different groups of semi-variograms. One are the bounded or transitional semi-variograms, and then we have also the unbounded or non-transitional semi-variograms. One classical form of a bounded is the linear variogram. We have first an increase that's covering the range of structured variability before we then have a breakpoint where the variance fades over to non-structured variance. That's the plateau. We also have a slight deviation from this linear model, and that is the curvy linear model. The most simple form of it is the spherical model, frequently used. So we have first an increase, and then we have a curve, and then above a certain distance, lag distance, A, that's the range, it becomes a plateau. similar forms, but a little difference in the equation that describes it is the exponential model. So that is a little flatter and goes and goes and goes, increases. And there's no particular boundary where this A coefficient describes. This is the transition from structure to random variability. Doesn't exist for the exponential and not for the Gaussian. So we cannot clearly, when we use the A in the equation, we cannot clearly say A is where we have reached the plateau for exponential and Gaussian. That's not the case.
Can you please again explain on the left-hand side of the slide that we on the left?
You mean this one?
Here on the-
I was not there yet. You are getting ahead of me. I first wanted to describe this shape where we have structured and then later a random variability. So now we go and look at the red curve here. We call this a pure nugget. In a few slides, we will see better what we mean by nugget. So the nugget is a variance component. So here, these models, they all begin at 0. But we have another, so we can describe this by an equation that we will learn in the next slides. And we have beyond this structure, so we have a basic structure or structure component, and that one is the nugget. On top of the nugget, we have this curve, or we can, so this one is probably a spherical model. We also can have on top of the nugget an exponential or a Gaussian model. Sometimes, so the nugget variance is, or the nugget coefficient in the model, which we will see in a moment, describes the extrapolated point and gives us the variance at the location. So the uncertainty or at the uncertainty of a point observation. On top of that nugget, it can move on, we get the structured variability. And then the nugget and that structural component, nugget is C sub naught, and the structured component is C, and here we have C plus C naught, that is then the sill, the plateau. So now let's get here to this case where we have a pure nugget effect. That is where from the shortest sampling distance already, we are at the plateau at the magnitude of the total variance. So we can say that data set whose semi-variogram looks like that red curve, pure nugget effect, that data set it represents a classically randomly varying data set. Pure nugget effect is what we assume for using Fisher statistic. Does anybody do the test whether observations in an experiment with randomized plots and using ANOVA fulfills the nugget effect? Nobody does that. For the exponential model, the structural component C is at approximately at h equal to 3 times a. So if we multiply this distance by 3, that's the point where we get the transition to the sill. And for the Gaussian model, the brown curve, it is 2 times a. We then also have unbounded or so-called non-transitional semi-variograms. One very simple form of it is a linear model that describes the experimental semi-variogram. Here we can say we are sampling a data set that is underlying or that reveals an obvious trend, like elevation data up, or like some soil textural data down a slope from top over back slope to foot slope. We have an increasing content of soil organic carbon. That increase with no plateau or no that increase without a stop in the organic matter content would just manifest the trend, and that goes with a linear semi-variogram model. Or we can have a power function. I have the equation for you ready in a moment. And this power function also shows us an exponential increase in the variance. Of course, no process in nature would have this behavior if we further and further expand the domain size. At some point, this would then probably fade out in something like this, and we may get a Gaussian function from it. Gaussian models can be found for data sets where we are doing well with sampling. We have very small differences over short distances, no big fluctuations. But then from a certain distance on, then the variance takes off. So that is why we have here this little so the little delay in the increase. So these are the general shapes. And don't forget, underneath each of these shapes of models, we can have the nugget, the C0 value. Here are the equations of these shapes. So pure nugget is just equal to gamma equals to 0 at h equal to 0, but then it is equal to C or equal to S square at h larger than 0. So at any lag distance larger than 0, we are at the plateau level. The linear model can be described with this simple equation. It's C times h over a for lag distances between 0 and h, and then C for h over h larger than a. That's that linear, that blue curve. The spherical model has to have also two components until we reach the range parameter a, so that particular lag distance where we have the transition. This equation is valid, and beyond that, it is just C, like here. The exponential model is given by the equation. Alternatively, so this is the equation that we use in our textbook. This is also the equation that R uses for the model. Alternatively, Deutsch and Journal, in their book, GSLib, Geostatistical Library, which is a very good book, they use a different equation. They have 3 times h over a. So when you use variogram fitting, make sure you check first with the software which of these two equations they are using, if the software descriptions, the manual does not say it per se. Run a simple test where you create a data set and you use this equation by hand and that equation by hand, and then you compare it with the shape of the curve that you obtain from the statistical package. And then you know which equation they are using. The same is true for the Gaussian form. So we are using this equation. Alternatively, Deutsch and Journal use this equation. They have this 3 in here. That makes a big difference. And when you compare your results with those out of the literature and you see discrepancies, then make sure you understand which of the two equations was used in the article. For the unbounded or non-transitional models, we use this linear function easy. So this is the slope times h. And for the power function, we use this equation, the same one, but we still have an exponent beta. In hydrology, there's a similar equation, and there this beta is called the Hurst coefficient, just for your information. Any questions to this point?
Is there any reason for the three original Deutsch and German?
I don't know if this was the original form. This was just done in their book 1997. This form existed way earlier. I do not know which one was there earlier and which came later. I don't know it. And I don't know the reason why it differs. I know, or I'm pretty sure a geostatistician would know it, why this difference was made. But Deutsch and Journal are pretty unique. So the whole R community that uses geostatistics and many others, they use the first. There's no benefit from it. Both models, so that this is only a constant, both models fit the data in the same way. The coefficients just look different. And you cannot, if you do a variogram fitting outside of R, and you get your coefficients for the model, and then you bring them into R, then you have to make sure that you're using the equation that R is using. So if you do the fitting outside in Deutsch and Journal's software, no, that doesn't work. Then you have to convert those coefficients first.
All this curve starts from 0. Just for the display, usually will not start from 0, isn't it?
You're right. Yes. I wanted to demonstrate to you here just the basic structure. But I also said, remember that all of these structures, here we see C, all of these structures can sit on top of a nugget variance. That is shown here. So this is that structure, but here we do not have C only, but we have C plus this nugget component. So I did not want to confuse you. And I want you to understand that the nugget is the first element, and then on top of the nugget, we have the structure. And the nugget is a constant. So I thought to explain you the shapes of the variograms, I don't need this constant. I could just eliminate it. And then we go from there. So we can put everything on top of it. And later today, when we come to nested models, we will even see that we can even use several structures on top. Sometimes for appropriate variogram fitting, a simple spherical model like this one would not be enough. We need to have a second structure on top of it, so we can add to this a Gaussian component. And then we have something like this going up here. I want to tell you up front that much, that why is that necessary? It is to have more flexibility with fitting variogram models for two variables at the same time. So there are some requirements for co-regionalizable, or for a model of co-regionalization. We need to have the same model structure and the same lag distance or range parameters for each structure, but the structural components can be different. That sounds very awkward to you, but we will go to an example where I explain in detail what I have just said. And I've also prepared a spreadsheet for multiple parameter fitting optimization. Model, a semi-variogram model fitting in co-Kriging, where you have to fit three variograms, can be a headache. It is very complicated. Here we see such an example of a spherical model. So here, and notice we are not starting at 0 for none of these three models. This is such an example of, for co-kriegung, for example. We have two variables, hydraulic conductivity, clay content, and then we have the cross semi-variogram, similar to the cross correlation that we learned yesterday. Here we have a cross variogram that has only one branch because both sides are symmetric if we use transect data, and in space there's no left and right branch. So that's only possible for one-dimensional data. So here, let me explain the structure. This one is the nugget variance, 0.043. Here, the nugget variance is 3.51. That's here. And for the cross variogram, the nugget variance is 0.148. So all have different nuggets. That's fine. Next comes C for the first structure. And from the equation that we have seen 2 slides ago, we know this is the spherical model. So this is the capital C for the first structural component. We call it C1 for the spherical model. And this one, 2664, is the first structural component for clay content. And this one is the first structural component for their cross variogram. And then all the other numbers in the model itself are identical. Well, this is given by the equation, the 1.5 and the 0.5. The only value that is optimized is the range parameter, A. And that is the tricky part. That range parameter, here it is 9 legs. That has to be identical for the particular structure in all three models. So all three models, variable A, variable B, and their cross semi-variogram have to have the identical range parameter, 9 legs here. And that makes it so tricky. And that's where we end up with getting no good fit. So they have invented then, or have come up with a solution. Well, let's add a Gaussian component to it. And here, the Gaussian structural component, that is C2, C sub 2, is here in this case 0.52. Here it is 3.328, and here it is 1.317. So all have different ones because they have different magnitudes and their variances differ. But they all need to have, for the Gaussian component, again, the same range, 20 legs. That needs to be fulfilled. Good geostatistical software does that. And if that is not obtained through fitting, then the good geostatistical software will knock on your door and there comes the error message. And when I was a beginner, I had no idea what that meant. Stepwise, I learned that. So I tell you right away. So that is then for the reason that a linear model of co-regionalization was not found, was not detected. Now, what is this linear model of co-regionalization? We describe variation in the landscape, variation of a process as a function of scale. So up to that distance, observations are related, and that can be described with a certain model. And if we add another one on top, that has then a variation of a different scale. That's difficult to understand right now, this variability at different scales. You might hold back a little or trust. So when we look at spectral analysis and other Fourier forms of variability analysis, then that will become much clearer what I'm saying here, or what I mean by saying we have variability that occurs at different scales. in that spectral analysis, it becomes very obvious that we have one component at a small scale varying, another component at a larger, and the third one at a very large scale. That's all on top of each other. And that makes our life so difficult if our understanding and our our observations do not tell us right away what's going on there. So fortunately, we have tools now that can filter, that can clean out the different scales of variance. And this condition needs to be fulfilled. That's one of the two, that we have these ranges the same. And that way, we have more flexibility in the fitting, and we get for all three variogram models, variable R, B, and the cross variogram, we get a good fit. The second condition we talk later about, that regards the magnitude of these coefficients, the nugget, C1 and C2, for all three models. They have to fulfill certain criteria. And that is the other difficult thing in the variogram model fitting. I've tailored a little spreadsheet that you can use for your own data in order to fit it. So I've uploaded that already to our Google Drive. We'll use that, learn it about it. Okay, any questions at this point? This goes a little ahead, but I wanted to tell you right away what I meant by we add different structures on top. So it's not only one curve. Well, it is one curve, but it can have different Legos in it. Now we want to identify or use the variogram to identify spatial domains with semi-variograms. So from looking at the range, at the shape of a variogram, and the magnitude of variance, we may identify the processes that go on in a domain. Let's say we look at this 20-hectare field, and where we sample these red points, the content, the soil clay content varies between 20 and 22%. In another part of the field, where we sample these blue ones, the clay content varies between 21 and 24%. So right here in between, but then getting much higher than here. And if we now cross these two domains, they are separated by this contour line. If we have one transect sampled that goes across it, well, then we have 20 to 24%, right? And this is the semi-variogram for the first one. So here we have 2 squared, that's the variance. And then in the second case, we have 3 squared. And in the third one, we have also 3 squared here. And then it further increases because we start with low clay contents here. And then we move on and we get higher and higher clay contents. And that gives us an unbounded semi-variogram. And that goes unbounded until we further increase the domain so that this one then comes back again. Here, a little more elegant version of it that we have put out in our textbook years ago. So this explains anisotropy, similar phenomenon. Here we have clay contents less than 18, 18 to 20, 20 to 30, 23. So this one could easily be a landscape that has a clear and obvious slope. This goes uphill, and these units are perpendicular to the contour lines, or sorry, they go along the contour lines. perpendicular to the main slope of the field. So highest clay content here at the tops where the good soil is eroded away, and then slightly decreasing. And in the valley, we have the lowest clay content, highest organic matter, and more silt. So different units give us different semi-variograms. And they are in this obtained for the same field within the same overall domain. It's interesting. So here we sample just perpendicular, we get this trend. And if we sample in this part where we have no trends because we are perpendicular to the trend, then we get nice bounded semi-variograms. Any questions at this point? Good. Then let us look at, so we have so far looked mostly at bounded semi-variograms. Here we now want to look at a few more. Here, again, our beloved soil temperature data from the first lecture. In east-west direction, that was where all the interesting stuff was averaged out, so very small variance. And here, look at the semi-variogram. We call this a pure nugget effect. So no structured variation. That's also what we found from the autocorrelation function that just dropped from 1 down to 0 before it hits the first lag distance. So that's what we observe here with the semi-variogram as well. So what information does the semi-variogram give us, or in what sense is the information different in the semi-variogram compared to the autocorrelogram that we have seen for the same data set? That also, well, I will draw it here for comparison. The autocorrelation function for that field for this data set was about this. So what information does this semi-variogram, the pure nugget effect, give us? In what respect is this different from the autocorrelation function? And what can we do with it? Very good. Exactly. That is the difference. What do we know from the autocorrelation function?
Starts from, say, 0.
Yeah. And what do we learn here? So there you said, yes, we see right away the variance, the magnitude of the variance. What magnitude do we see here on the y-axis? It's the autocorrelation coefficient. And can you give me an expression for the autocorrelation coefficient with a word that includes also variance? What is the correlation coefficient or the autocorrelation coefficient? What is it? Not quite. Not quite. So remember in the equation for the autocorrelogram, what was in the numerator? I quickly go back. This is the equation for the autocorrelogram. What is this? The covariance, yes. And what is R of H then? What type of covariance? It's the normalized covariance. Because, well, I said, when we were looking at that slide, I said that the covariance itself, people cannot deal very well with. They don't have a good understanding what the magnitude of it gives. And they cannot well compare different relationships between different combinations of variables. But if they have the normalized covariance, they know it must be between -1 and 1. And if it is larger than 0.6, they are happy. It is meaningful. It's high. They could not derive that simply from an autocovariance value. So that is the big difference. You have brought us to the right track. So the semi-variogram gives us the real variance. And the autocorrelogram gives us the normalized covariance, autocovariance. So that's the advantage of that. So here we see quickly the meaning, if it is high or low. And here we see the semi-variance in degrees centigrade squared. What can we derive from this? Well, we know our equipment's sensitivity. And if the sensitivity is about this magnitude, then we can forget about sampling closer. The equipment is not of a precision and sensitivity that we can use it for finer resolved measurements. If we are condemned to use this piece of equipment, then we just have to look for applications where the variance is larger. So we would need to go to a larger domain or to a domain that is more variable. Then our equipment is fine. So that's the good thing we can derive from the semi-variogram. Does it make sense to go for closer sampling distances, or do we need to expand the size of the domain to get larger variance? That's what we want to know, right? That's a good guidance for the next step when we explore where we go with our research. Good, now it works. So here, my colleague, Stefan Wirth, in Germany, and I sampled a transect. Overall, we get this mean, nice homogeneous data set, right? At one point was a bugger. Is that an outlier? What would you say? Looks like it, right? Yeah. These are the same data points in context of way more observations. So I just selected a very coarse sampling here for these red symbols, long distances, and there it happened that there was only one sample that was out there, and I would have had no argument with anybody about that being an outlier. If we look a little closer, then we find that in the neighborhood of that observation, all observations are that high. So it is not an outlier. It was just one representative of a process there. Would that disturb the semi-variogram calculation? Because the first legs, the variation, the difference to its neighbors of +1, -1, -2, +2 is the same as it is for this point, and so on. So it is not disruptive to the semi-variogram. The semi-variogram for this data set is what we have looked at earlier. So we used here a linear model to fit it. And that's the equation. Up to a distance of about 15 meters, samples of microbial biomass were spatially correlated. So here we have this nugget variance, and we were wondering, is it possible to decrease that nugget variance? We can use the semi-variogram to get the answer for it. I brought my pocket calculator, believe it or not. This is from 1982. I bought it when I became a student. Did all the statistics for my diploma thesis on it. It's a very nice Casio. It still works. It's a little brittle here, fragile, but it still works. So how do we know? So do you understand the question that I'm after? We were asking ourselves with the equipment, and Stefan Wirth had just got, it was a new institute in that landscape research center that was just opened up. And he got this nice infrared analyzer for microbial respiration and biomass and whatsoever. And we were wondering, well, we had, for pragmatic reasons, and because we had no clue what we were doing, we were wondering, we had this sampling distance of about 2.5 meters along a transect where we took many, many data points. Is it possible to further reduce this nugget variance by bringing it further down with even closer samples? So how do we do that? First of all, we need to look at the nugget value itself. This value here is 0.001 milligrams carbon per gram of soil squared. That's the variance term. So in order to get the average difference, we would have to multiply this 0.001 with 2 because of that equation, all that you cannot see, but that's the 2. So we have to multiply it with 2. That brings us to 0.002, and then take the square root of it. That is 0.05, almost 0.05. That's the difference, 0.05 milligram carbon per gram soil. That's the difference that we are looking at here at the smallest scale. And then I asked Stefan, hey, when you analyze the same soil sample over and over again, what is the difference that you have between parallel measurements? He did the test and he found, so this one was 0.045. Sorry. And the apparatus variance, or no, not the variance, the average difference between measurements was 0.015. That would give us the opportunity to obtain a nugget variance of 0.0001, so a value down here. So if we had decided we go back to that field and take samples at even a closer distance, we would have been so sensitive with the analytical device that we could have sensed differences of this magnitude. So that's an important thing, that if we strive for finer resolution, we have to make sure that our apparatus is sensitive to do it. So what does that sill mean at a distance of 15 meters? That sill, I mean this variance value up here. What does that mean? Or for all observations that are taken at distances larger than 15 meters. Well, the sill is at 0.0085, right? 0.0085. And we ask now, what would be the average distance that we can expect from observations that are sampled at 15-meter distances? What can we expect? That's an important thing to know. If I sample here and 15 meters further, what's the difference between both? That's what the semi-variogram informs us about. So this 0.0085, we need to multiply it by 2 and then take the square root out of it, that is 0.13. So we can expect that the value in 50 meters distance is 0.13 milligram carbon per gram soil different. We don't know whether positive or negative. But that's what we can read from the semi-variogram. It gives us an expectation of the difference between observation that we take some distance apart. That was also the original idea when Journal and Materon, another Frenchman, when they started geostatistics, and they used it for the mining, in the mining industry. They wanted to make their auguring, their coring for mines, for ores. They want to make it very efficient. So they used the semi-variogram. Okay, any questions? So these are very obvious and simple things, but many don't use it for this purpose. Another bounded, yeah, you have a question. Oh, yeah, thank you. So like we use the term experimental autocorrelogram, we also can use experimental semi-variogram. So the experimental semi-variogram are the numbers that we compute from the data. That's the experimental semi-variogram. The line or the curve that we use to fit it, that's the semi-variogram model. So in a similar way, when we get the autocorrelation function, these dots there, that's the experimental autocorrelogram. Yeah, then we call it semi-variogram model. Mhm. And some people say variogram only, but I prefer to say semi-variogram. Here, soil water content data. Again, those 140 data. We compute the semi-variogram for it. Oh, and here the nugget is 0. So there's no nugget in this model equation. And the rest of it is defined, is described with a spherical model. Here's C, 0.0012. And these are the coefficients. And we have a lag range where we switch from structured variation to random at 8 lags, at 8 meters. If we have a variogram beginning at 0, then sampling closer would not increase the level of information, would not make any difference. Here we use an exponential model for describing the experimental semi-variogram dots with a model curve from these data that we have seen before. So this is an exponential model. A form of a Gaussian model are these almond yield data that I've sampled as a postdoc in Davis in an almond orchard. So we have almond yields taken per tree, and at short distances, the semi-variogram remains calm. Down here, we have a nugget variance, and then from a certain distance on, the variance takes off. And we describe this with the Gaussian model. So you've seen now different applications for different model types. Here we want to decompose different sources of variance that are caused by spatial sampling design and local bulking. So we have a data set here collected. The basic interval was 5 meters sampling interval. This is, I think, in a study that I did before I installed capacitance probe access tubes in a field in Western Kentucky. I had no clue how close together I can put them out, how many tubes I needed to purchase to cover that landscape. Since I did not know whether 5 meters is not already at the pure nugget level, I had some points installed where I also took a sample a meter away from the 5 meter point. So every few points, I had an additional one that was 1 meter away. That's a nested sampling. Not enough with that. For each point, I took 2 samples in a cup to have the average then calculated. I measured the water content individually. I did not put 2 samples in a cup. I had 2 cups for each sample. And the mixing of the sample was done at the computer with the soil water content, averaging the soil water content. So each point value was a number that consisted of 2 measurements. Pretty weird scatter. Here, let's look now at the semi-variograms, how they change with the different scales. So if we look at the raw data set with a 5 meter sampling distance, this is the semi-variogram. One value up, but then the others nice continuous. If we use 1 and 5 meter sampling distances, we end up with a weird cloud of semi-variogram values. But this is what field data look like. I don't know of an R package that would allow you to do that. In R, we can set a fixed regular sampling distance. It's either 5 meters or it is 1 meter. But it would not allow us to use distances of 1 meter, 5 meter, 6 meter. Then the next would be 10 or even 9. Anyway, we have an assortment of distances. So for that, I wrote my own little computer code for telling the code, these are the lag distances for which I want the semi-variogram value to be calculated. And this is then the result of it. We can merge all those 1 meter sampling distances into the 5 meter sampling interval, because in the semi-variogram calculation, the model or the computer algorithm asks us what's the maximum lag distance. So all data separated up to 5 meters come into this class, and then an average weighted lag distance is computed for this class, and then the semi-variogram value is computed. So here we would not get a straight 5 meter lag distance. It would be less because we have also individuals that are only 1 meter separated. And then for the next higher class, it all goes up from 5 meters. So 5 meter, larger than 5 meter, up to 10 meters. And then here I have plotted all the number of pairs for the different scenarios. So if we have here the variogram scenario 1, scenario A, 5 meter sampling distance, all these blue symbols are the n's. So with each sampling distance, each 1 lag more, the number n of h decreases by 1. For scenario B, where we have these nested values, 1 and 5 distances, these are for all the possible lag combinations, the numbers. So very low numbers, sometimes very high numbers, but much lower than in the first scenario. That's why we have a wider scatter. Fewer samples. The smoothing effect is not so drastic, as we can see here, as for a larger aggregation. And for C, we have even more individuals, and the semi-variogram is the smoothest of all. So depends on the purpose, but if you are worried about scattery semi-variogram, combining different lag distance classes will make it smooth. Now here an example for unbound semi-variograms. We have infiltration data. In one part of a field, they are at a low level, then all of a sudden there's a jump. I don't know what it is. Could be a soil type change, could be a different history in management. So goes up, and the infiltration rate, the lag distance, the maximum lag for infiltration rate data is 24 meters. That is that much in the field. So it keeps to be increasing. Or here, relative water table elevation data. You know, data like this, like a watch glass, and the water table variogram up to 16 lags, that's about this one, gives us a big increase. Unbounded semi-variogram. Any questions to this point? Then let's move into two-dimensional semi-variograms, how they are computed. In principle, it is the same. And I want to stress the point here again. So it's not really complicated mathematics. It is just the multitude of steps, of simple calculation steps that you cannot finish on a sheet of paper. So here I have this little system of grid points. These distances are identical, 8 points. So first we want to find what is the closest lag distance that we can look at for between neighbors, and how much is it? So for the lag 1, lag class 1, the shortest distance, we call this interval 1. That's one lag. And we have number of pairs in that class. We just need to count them. When we compare these 2 points, these two, and so on, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 pairs in that shortest lag class. Now we go to class 2. Those are all the diagonals. Not much larger, but a bit larger. So all from your geometry, you know that all these, the length of all these green diagonals is 1.41. That's lag class 2. Simple calculation, 1 squared plus 1 squared, and then the square root of it is 1.41. Now the third lag class. These are the orange lines here. That is lag class, and the obvious average distance is 2. And how many of those do we have in this distribution? 1, 2, 3, 4. So we have only 4 neighbors. And then the over next, the lag class 4, is lag classes 4, that is calculated by 2 squared plus 1 squared, and then the square root out of it, that is 2.24. Oh, now it gets tricky to count all these. 1, 2, 3, 4, 5, 6, 7, 8, 9, I think. We'll see whether I counted correctly. So now we want to calculate the average lag distance. For example, if we combine classes 2 and 3, 2 and 3 were not that much different, so we want to combine these two. We have 7 neighbors, 7 pairs that are separated by a distance of 1.41. And for the lag class 2, we have, sorry, for lag class 3, we have 2 distance, but we have 4 of these orange lines, 1, 2, 3, 4. We sum these up and divide them by the total number of neighbors, and then we have the average weighted lag distance of 1.62. That's where the semi-variogram value will be plotted in the variogram versus this lag distance, 1.62. So it's not the average between 1.41 and 2. It's the weighted average between them. And because we have more pairs in class 2 than in class 3, the weighted average is closer to the average of class 2 than to the average of class 3. Simple, obvious calculation. Have you ever calculated weighted averages? Good. Then you need to tell me and say, hey, move on. Here's an illustration from the book of Deutsch and Journal. So we can have isotropic variograms. So I made no particular concentration, no focus on a certain direction. But of course, the landscape has different directions. So we can say, oh, we want to have this slope going in one direction, and we want to study the semivariance behavior up the slope, or we also want to study it perpendicular to the slope. Two different things. So here is how Deutsch and Journal, in their parametrization of semi-variogram models and also for Kriging models, then how they can narrow down the space, the search space from the search space for neighbors. So they have a certain major direction vector, that's the angle. We can predetermine the angle in what direction it goes. Then we have here a lag distance class. Let's say the X lag distance class is 4 units, but we can also have a lag tolerance of 2. So it's 4 units, but we allow a certain tolerance in that direction. And then we have a widening angle. So that is the tolerance here. We let it widen up 22.5 degrees. And then from here on, we reach the maximum bandwidth, which is 5. From here on, we do not allow it to widen up any further, but just to stay here. Because when we go further up, then we may run into the problem that here the landscape property changes already. If it does not, then we can just vary this one and let it go further up. But keeping one direction in mind, it's good to have this maximum bandwidth for a certain direction. And this is done for each point. So we are not narrowing it to this area in a field. This is relative for each point. The next point then would move the whole rocket shape up. So it's really complex modeling. It is difficult, and I have great admiration for the programmers who write those codes for these types of anisotropic variogram structures. The good thing about Deutsch and Journal is they were one of the first who provided online their Fortran computer codes for calculating all this. And their book looks pretty cryptic. So it came at the time when I bought it, it came with a CD, and there were all the source codes on it. And you had to know about Fortran. They had all kinds of different sub modules. You need to link different ones. So it was not a quick click. You were working in DOS, and then you were compiling your codes and then linking them. And they also provided graphics. It was all PostScript format. You may not know that anymore, but they truly knew what they were doing. But you couldn't be a beginner in programming to use the analysis. But they were very illustrative about it. They provided the codes, and one could dive deep in it. There's also another. So they provided later these codes also in WinGSLib. I mentioned that earlier on the first day that WinGSLib is still public domain available, but it is not supported anymore. But it's still downloadable, and I use it for a few things. We'll see an example later. There's also from the same group from Stanford, there's another good Windows-based package that is called SGEMS. It is, I would say, a little easier to handle than WinGSLib. The equations are the same, the routines are similar, perhaps based on the same codes even. So that is a good tool that is what I used in my class before R came up and offered a lot of good routines. You have a question? The lag tolerance is that you do not take a straight lag distance, but you can shift it. So it includes plus or minus 2.0 units to it. In a field that is not densely sampled, you may not have enough points in a lag class. So it allows then to look a little left and right. And 2 is pretty high. It's 50% of the total lag class. But if for larger lag distances, here 6, you allow 2, then it is not so much anymore. But you search a little farther than the lag class would tell you. That's meant by lag tolerance. So next, I want to switch gears here. UC Davis, there was once a scientist, and he did one of the first studies for spatial data analysis at a time, early 70s, early to mid 1970s, when nobody in soil science really had a good hold of geostatistics and their use. And they had this man go out and measure infiltration rate in a field, in a plot that was 160 meters long and 55 meters wide. And because they did not know how many samples to take, they used not a constant separation of these samples across the 55-meter unit, but they had some. So that would have been, so do it in 5-meter steps. That work effort would have been unaffordable. And they took measurements. So along of each 8 rows, 160 infiltration measurements were taken. So 160 in each row, every meter. 1,280 measurements, infiltration rate. No truck. All the water was brought into the field on a wheelbarrow. I've seen the field in 1990. Well, of course, not this experiment anymore, but it was a tremendous effort. And here, we want to look here at those column numbers and then identify what. So, of course, within each row, it was 1 meter distance. But through those row distances, we want to see how many different distances they captured. So one was the 1 meter distance, was here between 54 and 55. The second one was 5. There were more. So 0 to 5, 20 to 25, 25 to 30, 30 to 35. Those combinations were for 5-meter lag distance. 15 were 5 to 20, 20 to 35. And that was all. And then 19 was 35 to 54. And 20 was 0 to 20. And that was it. So 0 to 20 and 5 to 25. And where else were 20? 35 to 55. Thank you. And there was 24, that is 35 to 54. And 20, 25, yeah, 0 to 25 and 30 to 55. And 29 was 25 to 54. 30 was 0 to 30 and 25 to 55. 34 was 20 to 54. And 35 was 20 to 55 and 0 to 35. And so on. And 50, then 49 and so on. So you get the idea. Different numbers of neighbors, But since we have so many measurements within each row, it was a tremendous data set. And they started early with a less intensive sampling, and it turned out to be a pure nugget effect. And then the person who measured it turned around and said, well, I have to take closer samples. And then he continued measurements and took twice as many. And here is the semi-variogram of his analysis. And this is not a model that we are used to use now, far away from what I showed earlier. But in those days, they had no clue about spherical models, exponential models. They used an equation that they had been used in other physical behaviors in soil physics. So they just used this exponential and plotted the semi-variogram. And through those short lag distances, they got a very good idea about the small scale variability. That's important to have. So with this slide and also the following, I want to encourage you, when you have no idea about the spatial behavior of a variable, that you use your brain to design it as efficiently as possible, that you get, with least effort, you get the most out of it, and you know at least roughly what this behavior is. And then you go from there. And there's no blame in it and no harm with coming back from the field and having a pure nugget effect. There's blame if you then give up. So you can always derive then a strategy. What do I need to do next to derive the structure? And the numbers and the shape of variograms will tell you what you need to do. Here's another study that was conducted, I think, in Iran. It was a national survey of exchangeable sodium percentage. And the person who did the study sampled on a 1 kilometer grid 34,318 hectares and 34,318 hectares. So you can imagine, or you can calculate, how many samples that would be on a 1 kilometer grid. Any idea how many hectares are on a 1 kilometer grid? Oh, come on, you know that. How many hectares are in a 1 kilometer grid? Well, I'll let you figure that out. And the scientist thought 1 kilometer is a long, long distance. And he was used to field research, so he wanted to make sure that he was not missing the point. 1 kilometer sampling distance can easily result in a pure nugget effect. And you don't know what then happens if you are on a national survey and you need to come up with an answer. So he was wise to collect 18 samples just 1 meter away from the main sampling point. Here's the result. He got, for all those grid data, he got a variogram. And for his 1 meter distances, samples taken at 1 meter distance, only 18 of those many 1 meter away, and he could get a very good definition of the nugget variance. Smart thing to do that. So he could really direct this curve down here. Without this point, you would not know whether this curve is here or there or where is it. But you can sample for a good estimate of the nugget variance with this approach. Does anybody know now how many hectares are in 1 square kilometer? Good, thank you. And here we can use again the information from the semi-variogram to estimate what is the difference between samples that are taken over a certain distance. So let's say 2 kilometers. What variance can we expect over 2 kilometers? Well, we take our computational unit, and here the gamma is the semi-variance is 16.77. What do we do next? We multiply it with 2. That's 33.45. We take square root of it, and that's 5.8. So 5.8. That is the difference that we can make for samples taken over 2 kilometer distance. How about the nugget? Sorry, the sill, 21.6. What do I need to calculate? 21.6. Multiplied by 2 is 43.2. What do I need to square root? 6.6. So that's the expected difference for any sample taken farther than 4 kilometers apart from each other. That's a good information. Still 15 minutes, right? Good, thank you. Okay, so now the Hall effect. Have you ever heard about it? So that is something in the semi-variogram, and when I was beginning to learn this, to study this, I heard a lot of interesting explanations for it. It was, nobody had a good answer what the Hall effect really reflects. And we have to understand, in the same way as for an autocorrelogram, that the shape of the semi-variogram is affected strongly by the shape of the original data. So here we have a regular variance decrease. So it can be understood in a way that we can walk the increase in a semi-variogram. Let me make this little drawing here. This part of the semi-variogram manifests the simple fact when we walk down a line and we take samples. Taking more and more samples, the overall variance of the growing population will become bigger and bigger, right? At some point here, we come to a zone where the variance decreases again. So data will not continue to change in the same direction, either decrease or increase up to this point. But now there will be a repetition of what we sampled previously. So a lot of population individuals that we had earlier will now come back. And we may come into a zone. If we had up to here, we had an increasing trend, we may now come into a zone where we have a slight decreasing trend. And then after that, we may come again into a zone where it further increases. It's nothing more than that. That's what makes a Hall effect. And we can consider it as a way that will be important later for our spectral analysis lecture, that here's a maximum, here's a limit for one scale of variation. From that point on, the scale will not get any bigger. The variance will decrease until we get to another scale. And here at an even larger scale, we have a larger variance. So we have different scales of variation on top of each other, following each other. So that's the reason for a Hall effect. And here we have described this variogram with one component. So here, first of all, this is the nugget. And then this one is a linear component. And here we have a spherical model. And then on top of that, we have a cosine model. And here we used 30, 1 over 30. So that is the scale of variation, the cosine wave of 30. Coming down and then further up, the distance is about 30, from 10 to 40 to the next scale. So nothing mystic about it. We just have to accept that semi-variograms do not behave in the field like they do in the classroom and in the textbook. You see all kinds of awkward, weird behavior. Don't be surprised. But if it were simple, everybody would do it. Here, semi-variograms for our soil temperature data. Increasing and then reflecting the cyclic behavior of the original data. It will come down again and then again increase and come down. And this semi-variogram model cannot be described with a spherical, Gaussian, exponential, linear power model. No, it's a simple cosine equation. Softwares do not allow for that. They don't have that in their package. So it's nice if we can use an Excel spreadsheet and then fit the coefficients for that cosine model in there. So now, before the tea break, here's an exam question. Soil water content semi-variograms. And these semi-variograms were delivered from a climatologist, measured at weather stations, I think, from the Mesonet, one of the most famous networks of weather data in Oklahoma. It's a fantastic arrangement network. So how would you interpret these semi-variograms? The person who delivered these was Robock. I took them from the literature, from one of his articles. How would you describe these semi-variograms? Tell me what you would do it. You are the reviewer and you see this manuscript is still in review. And they've put these lines in here, the authors, as variogram models. So they want to use that for interpolation. So what are you going to tell the authors? Yeah, that is not a drama. So we see variance plotted versus some sort of distance. And you cannot expect that it is equally spaced, because the mesonet, it means there's a weather station in each county, and they are not on a chessboard pattern. They are irregularly distributed. So you understand what we are looking at, right? Is this good for spatial interpolation? Do you see a variability structure in, or a structured variance in the semi-variogram? Not really, no. Don't be so soft. No, you would say, what's the basic here? So there's no structured semi-variance. You can't do any interpolation on that. It's a pure nugget effect, right? Yeah, pure nugget effect. No, data useless. Until we find out the backside of the coin. I'll show you the right-hand side of that figure. Here is the autocorrelation function for the same data. What does that tell you? Looks weird, looks different from what we have learned, what we have seen here in class, what I presented to you. But that's, when you go out, you see it all different. But you need to know what you are looking at in order to understand it. And I hope the content of the class would help you to see now what is going on. So what do these autocorrelograms tell us? Do they make this looking better, or do they put out more question marks? Mm-hmm. Does anybody have an answer? How do you approach that? Then you ask yourself, in what sense does it differ from what I know, right? And we know from autocorrelograms that they start at a high level, and then at some lag distance, they drop. Do we see that drop here? No, we don't see it. To what distance are these covariance functions plotted? To a maximum of 30 kilometers. What's the length expansion of Oklahoma? Is that 30 kilometers? Much, much larger. I don't know exactly, but I would say probably 800 to 1,000 kilometers. So this is only the very, very first step of the autocorrelogram. And in their analysis, and these are excellent professionals, in their analysis, they said, oh, for the interpolation, we don't need all that long lag distance business. If we have our covariance function in our pocket, a good covariance function over 30 kilometers or even less, we are fine. We then can go ahead and do the interpolation, Kriging or co-Kriging. So this one is up to 1, and still after 15 kilometers, it's still close to 1. So if they had presented the autocorrelogram for the whole Stillwater region, it would have been perhaps to 100 kilometers. somewhere here, that function would have dropped to 0. And the same for little Washita micronet. So perhaps somewhere here, that autocorrelogram would be down to 0. And the same here for the Fort Cobb micronet. But they have just the small scale, the first few legs, and that's what they need for spatial interpolation. If I want to know what's going on here between these few tiles, I don't care of what's happening back there. I only need the best fit to a variogram model and have high autocorrelation for the first few legs. That is a good basis for making a guess, because that gives us a high level of confidence. The high correlation is the basis for a high level of confidence in a spatial interpolation. So they have then, for the same data, used these variograms for which they can use in Kriging. They can't use the autocorrelogram, but they have plotted these here to show our Kriged values. Well, these are not pure nugget effect. The variogram would later go up here to this level. At some longer distance, it would go up. But this is good. So the variogram is nothing else than giving a weight to the next neighbors. Giving a weight, the distribution of weights. And all the weights need to sum up to 1. So the flatter it is, the more equally the samples have a weight here. If the semivariance does not increase over the first few legs, that means the first few are equally important. So that's how the matrix in Kriging is solved. We will learn that in the coming lecture. But I hope that you get this idea before, and don't be surprised if you see something like that. And don't reject something that looks awkward to you. Try to look behind. That's very important. So if I had seen as a reviewer only this, I would have said, no way, no way, not good. But having this information, oh, that is going on. So how are autocorrelation function and semivariogram related? Not really, but similar. We can do this computation here. R of h is equal to C of h over S squared. And gamma of h is equal to variance minus C of h. And gamma of h is S squared. With that, then equal to S squared times 1 minus R of h. And that's yes. Force, yes, exactly. I said these equations do not work exactly. Only for second order stationarity. Yes, thank you for pointing at that. And then this gives the graphical representation of both. This is in an ideal world, which is not out there, which is not existing. So, and here some final remarks. Knowledge of semivariograms helps to design future experiments and sampling schemes. Analytical techniques that are appropriate for the sampling scale, sample size, and resolution can be chosen and evaluated with the semivariogram. Is the device appropriate? Can we still go to a smaller scale? Or is it not so sensitive and we just need to look for the big fluctuations in data? Semivariogram fitting, how do we define what is the optimum? Don't use R square. We will look into the fitting in the next 2 lectures. The important thing is first few legs give a good fit. Everything else is not as important. What comes next? Scale variance or scale invariance. So does the variance remain on a certain plateau, or from a certain leg distance, do we further go up? Or is there in between a Hall effect before it goes up? Do semivariograms change temporally? Oh, yes, like for the autocorrelation function. Soil water content is the biggest troublemaker in that. So semi-variograms for soil water change dramatically. And space-time semi-variograms. What is that? We've taken soil moisture content observations along a transect and over many times. So now we use as the x-axis in the coordinate system space, and as the y-axis, or the easting and northing, the northing axis is the time. And we can compare what time does it take to have the same variance of soil water content measurements that compares to a difference, soil water content difference measured over 5 meters distance. That's an interesting question. Okay, and now that's it for semi-variograms. And we are on time, ready for our tea break, right? Good. Thank you for your attention and the good discussions.